Hello, Calc BC. Welcome back. So today's lesson is on implicit differentiation. And this is a pretty exciting, important topic, and it kind of answers this question, like, how do I take the derivative of a non-function, so something that's not in the form y equals. And of course, when I mean derivative, which I really did not spell correctly, I of course mean the slope of the tangent line, also known as notationally dy dx. So that's the question we're trying to ask today. So for example, let's start with just a very basic equation, x squared plus y squared equals 25. As you guys probably know, this is the circle with radius 5. So assuming it's not a function, fails a vertical line test or somewhere like that, but we might still be only able to, or want to be able to find an equation for the slope. Okay, so here's what we got, x squared plus y squared equals 25, and our goal is to find an equation for dy dx, and it's going to be in terms of x and y, not just in terms of x like we're used to. Okay, so here's how we're going to do this. Basically, the process is we're going to take the derivative of both sides. So we're going to take the derivative of both sides with respect to x. And then by the chain rule, what we're going to do is when you take the derivative of y, you need to multiply by a dy dx. So when you take derivative of y, because of the chain rule, you multiply by dy dx. Okay, so let's go ahead and just do this. And so what we're going to do is begin by just taking the derivative of both sides of this equation. So the derivative of x squared is 2x. The derivative of y squared, you can think of it as like some function squared. The 2 comes down, so it's 2y. And then by the chain rule, we multiply by the derivative of y, which is dy dx. The derivative of 25, of course, is 0. So now that I've done this, what I'm going to do at this point is solve for dy dx. So I'll get 2y dy dx equals negative 2x. And then I'll get dy dx, the 2's cancel, equals negative x over y. Okay. And again, what that is that's the slope of our curve, the slope of like our tangent line. If you have the x and the y coordinates, you could plug them in and find the slope at that point. Okay, so that's what we're doing. You might be asking, like, Mr. Roach, why do we not multiply by anything when we take a derivative of x? Well, you kind of do in a sense, right? But like by the chain rule, what's the derivative of x? It's just 1. Like, the derivative of x is 1, so we don't necessarily need to put that in there because it doesn't change anything. But we do need the chain rule on the y, which is the derivative there of the dy dx. So if we have multiple y's, like we'll see in just a sec, we need multiple dy dx's. So let's do another example. Suppose we have 1 plus x squared y equals e to the 2y. So again, I'm trying to find the derivative. I'm going to begin by differentiating both sides. The derivative of 1 is 0. Here we use the product rule, and let's be careful here. So we have x squared times the derivative of y, which is dy dx, plus y times the derivative of x squared, which is 2x. And then on the right side, the derivative of e to the 2y is e to the 2y times the derivative of 2y. Derivative of 2y, of course, is 2 times the derivative of y dy dx. Now, you might feel like you're in a little bit of a pickle here because there are 2 dy dx's, but the good news is these problems are always solvable. So what we're going to do is get the dy dx's, get those terms on the same side. So I'm going to try and subtract over this x squared dy dx. So I'm going to subtract x squared dy dx. Okay, so I'm going to get 2xy equals 2e to the 2y dy dx. I'm just rearranging some terms. Minus x squared dy dx. Now, this is going to be a little weird, but just thinking like, once we've done that, we're going to factor out a dy dx. And by the magic of the chain rule, we're always going to be able to factor out a dy dx eventually and solve. So it's just like if I have, like x squared y minus 3y, you can factor out a y, and you're left with x squared minus 3. Well, I'm doing the same thing. So in this case, I factor out a dy dx from both of these terms, and I'm left with 2e to the 2y minus x squared. So that means that my dy dx, I'll just divide this whole thing over to get the dy dx on its own. So I get 2xy over 2e to the 2y minus x squared. Is this a pretty problem? No, of course not. But that's the strategy for how you're getting to that point. Okay, one more thing I wanted to show you, just kind of a nice little shortcut. So if I tell you, for instance, that 6 plus x cubed y equals sine of x times y plus 2x. And our goal in this problem is to find the slope at the point 3, 0. Okay, and of course, hopefully you read this, you see, oh, slope, they're asking me to find dy dx. So we have a point here, we have like an actual x and a y. But what I wanted to show you is you can take the derivative and then plug in the xy right away to solve for dy dx. So that's probably the cleanest way to do this problem quickly. So the derivative of 6 is 0, derivative of x cubed y is x cubed times the derivative of y plus y times derivative of x cubed. And on the right side, things get a little ugly, right? The derivative of sine xy is cosine of xy times x times derivative of y, plus y times derivative of x, and then the plus 2x, of course, that's a plus 2. But what I wanted to show you is, like, if we tried to solve for dy dx here, we could, right? We could factor this guy out and then distribute, subtract, and yada, yada, yada. But what I also wanted to show is you can plug in 3, 0 here. So right away, you could just take that and plug that in. So when I plug in 3, 0 here, for every single x and y, what am I going to get? Well, I'm going to get 3 cubed, I get 27 dy dx. The next term has a 0. And then we have cosine of 0 times x dy dx, so 3 dy dx plus 0 plus 2. And we see this worked out like really nicely, because this just gives us 27 dy dx equals, that's just 1 times 3, so that's 3 dy dx plus 2. And then we get 24 dy dx equals 2, so we can divide that out. So your dy dx is 2 divided by 24. Now, this obviously is like a hideous problem, and if you wanted to solve for the dy dx, you could, and you get the same answer, but it's a lot easier to just recognize it right away if they give you the xy value after you take a derivative you can plug in. Okay, thanks for watching. I'll have more in the next video.